Dear students, today's session is about interpolation. Let's get into the session. Consider a function y equal to f of x, where x are x0, x1, etc., xn, and y is given as y0, y1, etc. up to yn. So, what is interpolation? Interpolation is the process of determining value of y for any intermediate value of x. That is, it is the process of determining the value of y at any intermediate values of given x. For example, in the case of flight of a rocket, you can interpolate its trajectory. If you know the starting and ending points, you could get any of the locations of the rocket in between these 2 points. I hope you understood what is interpolation. That is finding the value of y at any intermediate value of x. Then what will be extrapolation? It is the determination of value of y for any x lying outside the given limit of x. It is finding the value of y or the function outside the boundary or the limit of x. And our topic of discussion is interpolation. For the better understanding or better performance of interpolation, we should have a thorough knowledge regarding operators known as finite difference operators. Finite difference operators. And their symbolic relations are also essential. So there are various types of finite difference operators. We are now going to see separately each of these operators, finite difference operators. So let us see one by one. So the first finite difference operator is forward difference. Forward difference, and is denoted by the letter or the symbol delta. For a given table of values xk, yk, where k is ranging from 0 to n, with equally spaced abscissa of y, abscissa, and the y is given as y is equal to f of x. That is that I had told you in the first slide, y equal to f of x, and y is varying from y0 to yn, and x is varying from x0 to xn. Thing is, these x and y's are equally spaced. And the forward difference operator is delta, and we are going to express this forward difference operator. So delta yi equal to yi plus 1 minus yi, where I equal to 0, 1, etc. up to n minus 1. This expression is very, very important. You have to learn the expressions of each finite difference operators. Now it's forward difference. So delta yi equal to yi plus 1 minus yi. Let's see. When I is equal to 0, delta y0 equal to y1 minus y0. Then what is forward difference of y1? Delta y1 is y2 minus y1. Similarly, delta yn minus 1 is equal to yn minus n minus 1. Remember, I can vary from 0 to n minus 1. Why? Because here the maximum limit is y's maximum limit is n. So that is our equation has to be end with yn minus 1. So these differences are called first differences. or first forward differences of the function y. First forward differences. Then you may think is there any second differences or third differences? Of course, there are first, second and third and end forward differences. Let's see. Similarly, the differences of first differences are called second differences, del 2. So del 2 is y0 is, instead of y1 y0, here you could see delta y1 minus delta y0. That is, second forward differences are the differences of first forward differences. Okay, so delta y1 minus delta y0. Remember here, first one is differences of the function itself, y1 minus y0. But here del square y0, or second del 2 y0 equal to delta y1 minus delta y0. And what will be del 2 y1 equal to delta y2 minus delta y1. So in general, you have to express it in terms of I. Del square yi is equal to delta yi plus 1 minus delta yi. So now you are in a position to generalize the the forward difference operators. So rth difference of y can be written as delta ryi equal to delta r minus 1 yi plus 1 minus delta yi. I hope you understood the first forward difference operator, that is forward difference operator, that is the first, second and rth forward difference operators. So remember these equations, first, second or third, and the generalized equation. And we can systematically tabulate and represent these difference. Important, we can systematically tabulate and represent these differences, and such tables are known as forward difference table or diagonal difference table. Forward difference table or diagonal difference table. So here in this table, each difference is located in its appropriate column midway between the elements of the previous column. Subscript remains the same in the diagonal. Let's see the table. Then it will be very easy. What is the name of table? Forward difference table or diagonal difference table. Let's see how it looks. So here you can see the forward difference table of given x and y. The given x is tabulated as x0 to x6 and y is y up to y0 to y6. So these are the given. So then you can see the row, first one delta y, del square y, del cube y, del 4y, del 5y, del 6y. First difference, first forward difference, second, third, fourth, fifth and sixth forward difference. Let's look one by one. So first forward difference. So that first one is delta y0. What is it? y1 minus y0. So we write it in midway between these y1 and y0. That's the delta y0. Then what is delta y1? Delta y1 is equal to y2 minus y1. So we write delta y1 in the midway between y1 and y2. Got the point? And what is delta y5? It is y6 minus y5. So that we locate delta y5 at the midpoint of y6 and y5. So now you got the point. That is, we can systematically represent the forward differences in a table where each difference is located in its appropriate column midway between the elements of the previous column. Okay. And then coming to del 2y. that is difference between delta y1 and delta y0. So it is in between delta y0 and y1. Similarly, del cube y, del raised to 4y, del raised to 5y. Have a look. What is del raised to 5y0? Del raised to 4y1 minus del raised to 4y0. So it is in between. Okay. Then del 6y0 will be del 5y1 minus del 5y0. So this table is very, very important. You should learn this table so that you can do the problems that we will discuss in this session. So that is, here you look on the table, the diagonal elements, subscript remains the same. Okay, subscript remains the same in diagonal. In the table, the first term y0, we won't tell x because y equal to. So that is f of x. So that's why the first term is considered as y0. And this y0, the first term in the table, is termed as leading term. And the differences are termed delta y0, del square y0, etc. are known as leading differences. These two terminologies you just remember, that's all. The first term y0 is termed as leading term and the differences are termed as leading differences. I hope you understood the table and the operator. Forward difference operator, its general form and this tabular form. So let's do an example, then it will be very easier for you. The question is, construct a forward difference table for the following values of x and y. You are given with values of x and y and I hope you can see it. X values are there and y values are there. Okay, note it down. And we are going to construct the forward difference table. What we are going to do first, x values of x are 0.1, 0.3, 0.5, 0.7, 0.9, 1.1 and 1.3. Then the corresponding values of y are noted down: 0.003, 0.067, 0.148, etc. up to 0.697. Sorry, you could see that y. Then what else? First difference delta y, second, third, fourth and fifth. Why I limited up to 5? Because you can see here. So let's see one by one. So delta y, first one will be between y1 and y0. So that is 0.067 minus 0.003. Answer will be this. Similarly, but you have to remember, you have to put it in between y1 and y0. That I had told you last slide. Remember to do. And then del square y, differences of first forward differences, del 3y, differences of second forward differences. And similarly, here you can see one very beautiful observation is here, that is del 4y is constant. You can see the 3 del 4y's are constants. Okay, so then what else? There won't be any difference between the values. That's why we limited there. So del 4y is remaining. So a previous column as a constant means the succeeding column difference will be 0. Got the point? Constant leading to 0. What does that mean? Yes, differentiation of a constant is 0. Differentiation of a constant is 0. I hope you understood. So that is, these are constant, and while you take the difference, it won't give you the value. That's why we limited this with delta 5y. So it's very easy. Forward difference table. So what is our topic of study? Interpolation. What is interpolation? Finding the value of y in between for any intermediate value of x. For understanding or finding such values, we should be very much aware of certain forward differences operators. And first one, this one, forward difference, first forward difference operator that we had seen. Okay, we should have awareness of these operators, and this session is all about understanding these finite difference operators. And the first of the finite difference operator is the forward difference operator. Okay, delta. So we are going to the second finite difference operator, that is backward difference. Here it is inverted delta. So again the same thing, that is the given values of x and y is noted, which is same from 0 to n, and y is f of x, and the backward difference operator is inverted delta. And how it is expressed? Delta yi equal to yi minus yi minus 1. The limits of I you should clearly follow. I ranges from n to 1. Okay, or 1 to n. No need of any confusion. 1 to n. Okay, there last time it was up to n minus 1. So that is, here you can see delta yi equal to yi minus yi minus 1. So let's substitute it one by one. So first backward difference, delta yi is equal to y1 minus y0. Then y2 backward difference, first backward difference of y2 is y2 minus y1. So first backward difference of yn is equal to yn minus 1. So understand the equation and learn it. Delta backward difference operator of y1, y2, etc. up to yn. I hope you are getting this. Let's move forward. Okay. Similarly, that for the last session, there are also second backward difference operators, which will be the difference of first difference. So del 2 y2 is del y2 minus del y1. Del 2 y2 is, sorry, y3 is del y3 minus, here this one is, this is y3. So del 2 y3 is equal to del y3 minus del y2. I am pronouncing del, it is backward difference operator, okay, or inverted delta. So in general, second backward difference operator yi is equal to backward difference, first for backward difference of yi minus 1. You can see the limits and then rearranging to get the kth backward difference. What is the equation? Generalizing k minus 1 yi k minus 1 yi minus 1. Okay, learn the equations because we are going to tabulate this. Of course, we can systematically tabulate and represent these differences just like the forward difference table. So this table is known as backward difference table. Similarly, each difference is located in its appropriate column midway between the elements of the previous column, and subscript of remains the same in every backward diagonal. There it is in the forward diagonal, this is in the backward diagonal. I hope you understood, and let's see the backward difference table. Yes, x values, y values, and first backward, second, third, up to 6 only. Here it is shown 6 backward differences. I hope no need of explanations. y1 minus y0 will be backward difference of y1, and you have to remember to write in between y1 and y0, and the same procedure for all the others. Difference is, here there is no del y0. Last time For forward backward difference, it starts from 0. Just compare and learn. It will be very easy. Now you just hear and understand. So this is the backward difference table. I hope you noted down or understand it. And let's see a third difference operator, which is known as central difference operator. Central difference operator, and is denoted by yet another delta. Okay, this form. In some applications, we have to follow this finite difference operators. Now we are going to see the third finite difference operator, that is known as central difference operator, again denoted by delta, this but small letter delta. So then you can see that the subscript of delta y for any difference as the average of the subscript of two members of the difference. Let's see. Subscript of delta y, central difference of any function of any difference, is the average of subscripts of two members of the difference. For example, y1 minus y0. The subscripts average 1, 0. 1 plus 0 divided by 2 is half. So the subscript is remaining as delta y half. Got the point? So y2 minus y1. So what will be the subscripts? Delta y 3 by 2. 2 plus 1, 3 divided by 2. So this is average is 3 by 2. So that's why subscript of the central difference operator for any difference is the average of the subscripts of two members of the difference. Therefore, delta y half is equal to y1 minus y0. Delta y 3 by 2 equal to y2 minus y1. So generally what will be, if you put delta yi, then it will be equal to yi plus half minus yi minus half, because I plus half plus I minus half, 2i divided by 2, so that is becoming I. Similarly, here this is the first order central difference, and similarly for higher orders, del square will be, of course, differences of delta. So that is again del square yi is equal to delta yi plus half minus delta yi minus half. You understand one thing, the direct differences are the first difference, second difference will be differences of the first, third will be differences of the second order, like that way. It's like a series. So delta n yi is equal to delta n minus 1 yi plus half minus delta n minus 1 yi minus half. It's very, very easy. You just understand the symbols and the terminology. So this is the third finite difference operator, that is the central difference operator. So central difference table, it's easy. y1 minus x is x to x6, y6. Here what will be y1 minus y0 will be labeled as delta y half. For the second one, yes, second 3 by 2 plus 1 by 2 is 2. Again divide by 2, it will be 1. So average, the subscript will be average of the subscripts of difference terms. So the higher order terms, have a look, understand. And while you look on to the table, you can observe that all the odd differences are fractional. You can see odd differences are fractional suffix, have fractional suffix, and all the even differences, it is not fractional, it is an even number. And also one more thing, for the even differences, the same subscript lie horizontally. Let's look, this y2, del square y2, they are horizontal. are horizontally located. This del raised to 4y2. So y2s. So y4 similarly. Horizontally, look on horizontal lines. Y4, you could see on the same line, you could see del square y4, and here also again on the same line you could say del raised to 4y4. Just an observation, no much very significant, but it is an observation that all the even differences are lying with the same subscript. All the even differences with the same subscript lie horizontally. So this table of representation of central difference operator is termed as central difference table, and I hope you understood the table. I will look on to the table carefully and understand it. Now let's see another notation of this finite difference operator. My dears, the finite difference operators are more are there. We are just in between, just seeing an alternate notation for doing some problems, that's all. So alternate notation, let a relation y equal to f of x. Just understand things. Y is given as f of x and x values are x, x plus h, x plus 2h, x plus 3h, etc. Y will be y plus h, y plus h, etc. And another notation, this first forward difference operator delta yx is equal to, what will be, instead of I, here I write x, so then this will be s yx plus h minus yx, and this can be written as, since y equal to f of x, then yx plus h can be written as f of x plus h. That's all. That is the notation. So yx plus h is minus yx can be written as f of x plus h minus f of x. So then difference, second difference del square y of x is equal to del yx plus h minus delta yx. Similarly for backward difference also we can write the same way. Instead of yx minus h, we can write the f function form. That's all. Since y is equal to f of x, you can write every yi as f of I. Got the point? yi plus 1 as f of I plus 1. So y x minus h is f of x minus h. That's all. That is another notation. So similarly, central difference operator delta yx, so it will be the average value of x plus h by 2 and x minus h by 2. Okay, so this can be written as f of x plus h by 2 minus f of x minus h by 2. Just another notation of finite difference operator. So I hope we had seen three finite difference operators. One is forward difference operator, second backward difference operator, third central difference operator. Now the fourth one, shift operator. So again, let y is equal to f of x and x having values from x plus h, etc. y plus h, etc. How can we define the shift operator? Shift operator is denoted by capital E. So capital E into f of x is equal to f of x plus h. Very simple. What is shift operator? The word itself giving you the idea. When the shift operator capital E operates on the function f of x, the result will be the next value of that function. X next value is x plus h. So that is, it will give shifted one step ahead. Okay. So when the shift operator capital E operates on the function f of x, the result is the next value of the function. Here we can term that it's a shift operator. Okay. If we apply twice a shift operator, means it will give you the value of the function 2 steps ahead. Okay, so one time shift operator means it will give you the next immediate value. One more time means it will give you the second value or the second succeeding value. If it operates n times, it will give you the nth value. Got the point? Shifted n times, n steps ahead. Okay, so e square f of x means e into e of f of x. E of f of x is f of x plus h. Again, e of f of x plus h is f of x plus 2h. So, generally, en f of x is f of x plus nh. I hope you understood. Shift operator. Shifting, yes, the operator to find out the next succeeding values step by step. Okay, so this is the fourth finite difference operator. And en, so that is a new notation that we have already had seen. I had shown you an alternate notation. So en y of x can be written as y x plus nx, nh. So en f of y of x can be written as f of x. So that is en y f of x e raised to n f of x is equal to f of x plus nh. Got the point? No need of any confusions, just writing directly. So what does means a shift operator operating on y0? What will happen? It will give you the value of y1. E to y0 will give you the value of y2. E4 y0 will give you the value of y4. Step ahead. Got the point? So then e square of y2. Remember e square of y2. So 2 step after y2. What will be that? y4. Got the point? So this we had seen shift operator in the forward direction. So in the inverse direction or the reverse direction, the operator is termed as e raised to minus 1. If it is e raised to minus 1, it will give you the value one step behind value. So that is e raised to minus 1 f of x is giving you, yes, f of x minus h. So e raised to minus n f of x will give you the value f of x minus nh. I hope you understood. Forward and backward direction of shifting, but one by one, that's all. So this is the fourth finite difference operator, that is the shift operator. And we are coming to next operator, that is average operator, mu. And average operator is defined as mu f of x is equal to half of f of x plus h by 2 plus f of x minus h by 2. Instead of function, I can write in terms of y. Okay, you just understand the expression, that's all. When an average operator is operating on the function, it will give you the average half of two succeeding values, that is f of x plus h by 2 plus f of x minus h by 2. F of x, you just see f of x, this x is average of x plus h by 2 and x minus h by 2, that's all. This is the average operator mu, and I rewrited it in terms of f and then y, that's all. That is the another finite difference operator. So coming to the last finite difference operator, which is the differential operator, capital D, and it will give you the differential value of f of x. So capital D f of x means first differential d by dx of f of x, that is can be written as f dash x, and d square f of x means, yes, second order differential of f of x, f double dash f of x. So that is differential operator. Differential operator is also a finite difference operator. So these are the how many we had learned. These are the finite difference operators. First one is forward difference, backward difference, central difference, then average operator, shift operator, and differential operator. So total 6 operators we had learned today. So we are just finding out some equation to do some problems. You just have a look onto this equation. We had seen these all term symbols: delta, inverted delta, small letter delta, E, mu, D. What are they? First, finite, forward, backward, central, shift, average, and final, differential operator. So we can deduce some relation, that's all. So delta yx, you remember delta yx, that is the first forward difference, can be written as y of x plus h minus yx. Am I right? This in terms of y of x plus h can be written as shift operator. In terms of shift operator, what is y of x plus h? E into yx. That means y of x plus h is the next value of yx. So that is, this is e yx minus yx. So that is taking this yx common, e minus 1 yx. That is, you could see that delta is equal to e minus 1. This equation is very, very important for doing the problems or for the next topics of your study. And similarly, backward difference and the shift operator, how they are related, you just write the backward difference relation for delta yx. Yes, yx minus y of x minus h, yx minus, what is f of x minus h? It is the back value of yx. Am I right? Since it is minus. So that is e raised to minus 1. This is raised to only e raised to minus 1 y of x. So taking yx common, 1 minus e raised to minus 1. And then doing simplification, this can be written as e raised to minus 1 can be written as 1 by e. So that is backward difference operator is equal to e minus 1 by capital E, where e is the shift operator and this is the backward difference operator. These two operations, these two equations are very, very important. I hope you understood, and thank you all for your patient listening. And today we had seen all these finite difference operators. I hope you enjoyed the session. Thank you all for your patient listening. Thank you.